Since it was opened on May 27, 1937, the Golden Gate Bridge has served as a transportation facility to the people of the San Francisco Bay Area, a structure spanning the bay and linking the population on both sides. It is estimated that over 500 million vehicles have passed over the bridge since 1937, and the traffic flow continues to increase. Although an ongoing maintenance program protects the bridge from the elements, the saltwater atmosphere still takes its toll. An inspection of the bridge starting in 1968 revealed that the roadway slab was extensively cracked and that it had separated from the supporting stringers in many locations. In 1978, the Golden Gate Bridge Highway and Transportation District decided to replace the bridge roadway. Although it would be very costly and difficult to replace, cost studies indicated that replacement was more cost-effective over the long run rather than repairing the original concrete deck. It was decided to undertake a prototype project to test the feasibility of proposed prefabrication and deck replacement procedures. The final concept design for replacing the roadway proposed that it be replaced in sections. The chosen sections are called orthotropic deck sections. The orthotropic deck consists of a flat, thin steel plate stiffened by a series of closely spaced longitudinal ribs at right angles or orthogonal to the floor beams. As the rigidities of the ribs and floor beams are of unequal magnitude, elastic behavior is different in each of these two main directions. This phenomenon may be called structural or technical anisotropy. Because ribs and floor beams are orthogonal, and because in both directions their elastic properties are different or anisotropic, the whole system became known as orthogonal anisotropic, or briefly, orthotropic. The orthotropic design replacement scheme was chosen for the following reasons. 1, the orthotropic deck weighs less than precast lightweight concrete or concrete filled steel gratings, thus reducing stresses on the main cable and suspender rope trusses, in addition to reducing tower and foundation stresses during a seismic disturbance. 2, the orthotropic deck will, with proper maintenance, last almost indefinitely. And 3, maintenance costs are much lower than with the other schemes. The construction phase of the contract began at a steel fabricating yard located in California. The fabricators were faced with the task of fabricating the prototype deck sections to the rigid requirements of the contract specifications. The initial fabrication step was to longitudinally join two plates, approximately 7 1/2 feet wide by 50 feet long and 5/8 of an inch thick, making one large plate 15 by 50 feet. As the picture illustrates, the fabrication of the deck section is conducted while the section is upside down. The subfloor beams, 3 per section, are welded onto the deck. One subfloor beam was welded on each end and one in the middle. The 6 longitudinal rib sections were then welded onto the deck plate. Each rib section is comprised of a 20-foot and a 5-foot section welded together to produce a complete rib section 25 feet long. To ensure the correct placement of the rib sections, a backup bar was welded onto the subfloor beam at the location where each rib section was to be positioned. Once the rib sections were correctly placed, they were tack welded to the deck plate surface. Then the whole unit was tilted on its side at a slight angle where the final welds could be completed, using a large submerged arc welder, ensuring weld strength and reliability. Each weld was inspected thoroughly, using a radiographic non-destructive testing technique that enabled the fabricators to detect flaws, ensuring that the welds met the requirements of the specifications. The steel pedestals used to secure the deck section to the bridge were fabricated and bolted to the deck during the final stages of fabrication. Temporary stringers were fabricated to provide support for the existing deck. These stringers had to be properly aligned, and this was done in the fabrication yard. That completed the orthotropic unit with the exception of sandblasting, painting, and the laying of the 1 1/2 inch asphalt surface. Nighttime approaches and preparations are underway for the prototype deck replacement. A vertical view of the bridge indicates the location where the prototype replacement takes place, approximately 1/8 of a mile north of the Marin Tower. The roadway itself is 60 feet wide from curb line to curb line. One important aspect of the process to note is the reasoning behind the decision to replace the roadway at night. The replacement is a challenge in itself, but added to that function is the problem of traffic control. Replacement of the deck would be easier if it were not for the constantly moving traffic. The bridge cannot be closed to commuters as commute traffic requires the full roadway capacity. So the replacement work must be done at night, between peak traffic hours, with each section in place by 5:30 a.m., with at least one lane in each direction open at all times. The replacement of the 3 sections took place over a 3-day period, with one section being replaced each night. As the starting time drew near, preparations for the bridge work began with the setting of traffic cones, routing the traffic to the edges of the roadway, away from the work area. A crane was then moved into the work area to place temporary barrier railings along the edges for protection of workers from the steady stream of traffic, and to ensure that automobiles did not drive into the void that was created when the existing deck was removed. In order to remove the original deck, the old concrete sections had to be saw cut from the rest of the roadway. A portion of this task was completed on a night prior to the first section placement. Before saw cutting, the prefabricated temporary stringers were placed under the existing deck to provide proper support. These stringers were used later to provide continuity between the new section and the existing deck. At the same time, holes were core drilled through the concrete to allow the contractor to place high-strength threaded rods through the existing deck and attach them to the deck stringer. Finally, preparations were underway for the deck replacement. The remainder of the saw cutting was completed, separating the concrete slab from the rest of the roadway. The reason for cutting the slab into 2 sections was to reduce the weight that the cranes would have to lift. The old deck weighed over 1 1/2 times that of the replacement section. The crane slings were attached to the concrete slab by way of high-strength rod connectors running through the previously drilled holes, and the actual replacement was ready to begin. The construction foreman coordinated the crane operators, and the first half of the concrete slab was lifted off the floor beams and hoisted onto a flatbed trailer which had been pulled to a spot right next to the work site. The process was repeated to remove the remaining half of the old concrete section. After placing it onto the truck bed, the slab was secured and driven away from the work site. As the orthotropic section was hauled onto the work site, workers prepared the bridge for the placement of the new section. The semi-permanent stringers that held the sawed concrete slab were removed. The pads on which the pedestals rest were cleaned and smoothed. The holes for bolts attaching the new section were reamed to ensure proper alignment. The area was now prepared for the insertion and placement of the orthotropic section. The method used to place the new section was the same as that used to remove the old section. Few problems were encountered when the new section was lowered into the roadway opening. The engineers and construction crew had done their work well. The job was highly successful due to good planning and a coordinated work effort, and the workers got faster and more efficient on each successive night. With this information, the Golden Gate Bridge, Highway, and Transportation District was able to make more accurate decisions with regard to the full replacement, which is expected to take about 3 years at an estimated cost of around $52 million, with the federal government paying 80% of the cost and the Bridge District 20%. The outlook is good that the Golden Gate Bridge will last longer than its intended lifespan. The fact that a deck replacement project has been undertaken will only increase the bridge's durability. A roadway across the San Francisco Bay is part of the state's commerce and is an integral part of the state's transportation system.